every single ion desires to reach its equilibrium potential as long as the permeability of the membrane is high enough for every single ion. Now, in the case of potassium, we calculated an equilibrium potential around minus 90 millivolts. Now, we have here an action potential in an air fiber. At rest, we have minus 90 millivolt, which means that resting membrane potential is quite close to the equilibrium potential of potassium. This also means that potassium is already at equilibrium at rest. Sodium, however, is a completely different situation. We have an equilibrium potential for sodium around plus 61 millivolts. You see, we are far away from the resting membrane potential. This means once the sodium channels open up, sodium has a very large driving force. Sodium ions will rush into the cell. Okay, now let's get started. Voltage-gated sodium channels. In the membrane, we have voltage-gated sodium channels. A voltage-gated channel means that it has different states, can be either closed or open. The conformation of this channel depends on the voltage of the membrane. We have here 3 different states for sodium. I have here different asterisks, different colors, coding the different states. So please just follow through. We get started at minus 90 millivolt. This is where we are now. We have an activation gate, you see. It's closing the entrance of the channel. So the channel entrance is closed. Sodium has a very large force, remember. It would like to go through. However, it is prevented from going through. Why? Because the activation gate is closed. Now we excite the membrane here. You know, we have different types of excitatory signals, which I have discussed in previous parts. We raise the membrane potential to, say, minus 60 millivolts. This is the so-called threshold potential. At this threshold potential, we have already induced a conformational change of this voltage-gated sodium channel. So now the activation gate is open. The entrance of the channel is also open. So sodium will rush through. Okay, so this is the case between minus 90 to plus 35 millivolt. So this is what causes the depolarization and then the overshoot. We go all the way up to, say, plus 35 millivolt. Once we get to plus 35 millivolt, okay, so you see the sodium ions go into the cell and they keep going in until we reach about 35 millivolt. Now, at this point, the voltage induces conformational change of this channel. So now it closes again. The way it closes is the following. We have here the inactivation gate at plus 35 millivolt. The inactivation gate closes the channel. So now sodium can no longer go into the cell through this channel. Okay? I have here all the notes for you. Very importantly, the permeability of the membrane increases between 500 to 5,000 fold. This is amazing. At the same time, take a look at the time. About the speed of this channel is mind-boggling. Here, the inactivation gate closes a few 10,000ths of a second after the activation gate opens. This explains why the action potential in an air fiber is extremely fast, as you can see here. Okay? Both the opening and the closing of this channel is amazingly fast. So, I have here another note for you. The inactivation gate will not reopen until the membrane potential returns to or near the original level of the resting membrane potential. Here we go here. See? Between plus 35 to minus 90 millivolt. This is this phase here. Okay? This is the third state. Okay? So now let's take a look at the voltage-gated potassium channel. Remember, In the case of the sodium channels, we have 3 different states. In the case of the potassium channel, to simplify it, we have 2 states, closed and open. I have here all the nodes for you. I'll discuss all these nodes, and then I have the summary for you here. So minus 90 millivolt, remember, resting membrane potential. At this potential, these voltage-gated potassium channels are closed. Now, we have the depolarization, remember, was achieved by sodium going to the cell. We go all the way up to plus 35 millivolt. Now here, sodium ions close. Remember, sodium channels close. Now at this point, almost simultaneously, we have an opening of the potassium channels. You see here, we have a slow activation of the potassium channels. They open up at plus 35 millivolt. Remember, this was also the voltage at which the sodium channels close. What this means is the following. We close the sodium channel and open the potassium channel at the same time. Now, this is incredibly effective. Why? Because this means that we can repolarize the membrane potential very quickly. Okay? So now I have the notes for you to summarize. In the case of the voltage-gated sodium channels, we have 3 states, 1, 2, 3. In the case of the potassium channel, the voltage-gated potassium channel, we have 2 states. I hope this was helpful.